Almost all of science is comparison. A study is compared to other studies. A theory is compared to a measurement. Measurements are compared with each other. Comparison everywhere. Near the beginning of modern science, with Newton and the apple, two square law functions were compared. Newton's new postulated gravity function was compared to the established centripetal force function. The new function had the distance squared, the other had the velocity squared. For the Moon, both functions gave almost the same result, indicating that the Moon was held in orbit by Earth's gravity. Here, one number from a scribbled calculation was compared to another single number by a bored young man looking at an apple tree. One rough number, then, has led to lots of numbers now. It could be said that science is the manipulation of data sets of numbers. There are data sets of measurements, data sets from functions, and data sets from other published work. Usually a measurement data set is an experiment, and a function data set is an hypothesis. While the functions in real experiments can be very complex, three simple functions are almost always of interest. The linear function, the most used of all functions, the exponential or square law function, as in Newton and the apple, and cyclical functions, sine and cosine stuff. There are lots of statistical tests for comparing data. Each test is useful. All the tests are a challenge to understand. Here, the goal is to reduce mathematics to a few simple, understandable tools. The correlation coefficient, the Correl function in a spreadsheet, is one of the most powerful simple tools. It is easy to compare data sets using the correlation coefficient, and it is possible to think of the coefficient as the probability that two data sets are related. Unrelated data sets give 0. The correlation coefficient gives a 1 if two data sets zig together, and a -1 if one zigs while the other zags. In using the correlation coefficient, the linear and square law comparisons are the easiest. First, build simple linear and square law functions the same length as the data set. Then compare the data set with each simple function using the correlation coefficient. A column of counts in a spreadsheet, 1, 2, 3, etc., gives a linear function. Another column of squares of the counts, 1, 4, 9, etc., gives the square law function. The Correl function gives the coefficient. Here are 10 scumbled up values slightly randomized from a linear function. Set up a simple linear function with a count from 1 to 10. Set up a simple square law function by squaring 1 to 10, getting 1 to 100. The correlation coefficient between the data set and the linear function can be thought of as a probability that the trend is linear. The correlation coefficient between the data set and square law function can be thought of as a probability that the trend is exponential. Here is a scumbled up square law data set. For inverse linear and inverse square, the correlation coefficient will be negative. Because inverse square and inverse linear functions have the same basic shape, they have similar comparisons. The negative comparisons, therefore, are not as good as the positive ones. Inverting a data set to make the coefficient positive will give more usable results. The rule, then, would be to invert the data set whenever the coefficient is negative and try again. Here is a famous data set with 144 values. Here again are the steps to the analysis. First, set up a column with a count from 1 to 144. Next, set up a column with the square of 1 to 144, which ends at 20,736. Use the Correl function to get the correlation coefficients. The linear coefficient is 0.87. The square law coefficient is 0.94. The exponential or square law coefficient has the highest probability. Here are the best fit linear and square law curves produced by the spreadsheet LINEST function. The exponential function pretty obviously looks the best. This is a representation of world temperature since 1880, derived from the GISTEMP database on the giss.nasa.gov website. The 0.94 probability indicates that the temperature is increasing exponentially instead of linearly. Welcome to the real world. Since everything from gears to planets go round and round, cyclical function analysis is essential. Analyzing a cyclical data set is more complex than analyzing the linear or square law data set. The linear and square law functions have amplitude only, while cyclical functions have three parameters: the amplitude, the frequency, and the phase. The comparison needs to be done against cyclical functions of different frequency and phase to get usable information. The standard way to solve this problem is with the FFT or fast Fourier transform. While the math for the FFT is complex, it is possible to get a simple version of it with the easy-to-understand correlation coefficient. It really is just a matter of comparing the data set to a series of sine and cosine functions of different frequency. By comparing the data set to both the sine and cosine, it's possible to get an idea of the phase. Here is a slightly randomized cyclical function with a frequency of 2 and phase of 0. Here are the sine and cosine coefficients for frequency 1, 2, and 3. The highest probability is for a sine of frequency 2. Here the phase is 90. Here it's 180. The frequency is always 2, but the highest coefficient shifts from sine to cosine and positive to negative. This shows the principle with only 3 frequencies and the correlation coefficient. An actual FFT transform usually has 1,024 frequencies. More about the extremely valuable Fourier transform and Joseph Fourier, the Napoleonic genius who pioneered it, are too much to go into here. While serious work for scientific peers needs math tools that will impress scientific peers, common sense work for ordinary people should be done with tools they can understand. Statistics, the lifeblood of science, is the domain of the college-educated. Even with the expensive educations, many don't trust it. As it is true that games can be played with statistics, some mistrust is good. The less you need to understand, however, the more trustworthy the result. I say the 4 most trustable tools are the mean, standard deviation, confidence interval, and correlation coefficient. I think they would be trusted better if called the average, average error, average, error with sample size, and comparison probability. Or even better, call them average, error, improved error, and comparator. While many with graduate degrees don't know them, the 4 things on my list of statistical tools can be understood and used by 12-year-olds. The narrative of science for scientists is couched in statistical language. The narrative of science for everyone else is, look at the complicated and cool thing we've done. You'll have to just trust us that it's correct. Between the eye-glazing professional and the untrusted gee-whiz popularizer, there is a largely unexplored middle ground, where simple results and easy math lead to conviction of truth. We can find the distance to nearer stars using just a digital camera and filter with only square law math. The Earth can be proven a globe by driving a smartphone south and calculating the radius with a simple linear function. I even made a wonderful poem about calculating the radius of the Earth. The radius is 60 nautical miles for 1 degree times 57.3. One of my best efforts, if I must say it myself. Simple names for mathematical things are important too. The term correlation coefficient will cause most conspiracy theorists' eyes to glaze over. Calling it the comparator, comparison formula, or comparison probability gives the scientist a chance of being heard. Even better, calling probability odds and expressing it as an integer from 1 to 10 makes everything seem easier and more trustworthy. The odds are 9 out of 10 that climate change is exponential. It's more comfortable than the estimated probability of quadratic nonlinearity of distemp temperature anomalies is 0.94. If it were understood that most of statistics, and therefore of science, can be done with just 4 simple tools, even conspiracy theorists, journalists, and lawyers might manage to learn them. I imagine that might be painful. Thank you.